Here we go to the heart of what we're going to be doing with bell-shaped distributions. We're going to find probabilities on the curve for intervals. So the normal distribution is symmetric, bell-shaped, and characterized by its mean, mu, expressing the center, and standard deviation, sigma, expressing how much it varies for the values under that curve. The probability of observing values with any given number of standard deviations is the same for all normal distributions. So that means for any mu, for any mean, and for any sigma bigger than 0. If the sigma is equal to 0, it has absolutely no variation, and it's never negative. So here they show a picture. You should see this is familiar. It's the empirical rule. And actually the empirical rule rounds things off a little bit. So when it says something like 68% or 95%, it's not exactly that. We're going to be doing more exact things. So we're going to look at women's height, and if we know that the true average height is 65, and I'm assuming this is inches, and the standard deviation is 3.5 inches, and the average height for men is 70 inches, and standard deviation is 4 inches to the nearest tenth. The height of these two different bell curves hasn't got anything to do with the height of men or women. That is actually a count. Remember, a histogram has a count, and a histogram approximates the curve. So this is basically saying that there are more women around the mean who have that height than there are around men who have a mean. So if I'm looking, let me click this to get the cursor showing. So right here around 65, there's a lot of women who are that height. If you look at men, there's a lot of men who are that height. But there are more women who are that height than there are men who are that height. Hopefully that helps you a little bit. So when we look at this in terms of a particular distribution like the height of women, we're going to put numbers in there. But we typically want to look at the standardized one where we have 0 as the mean, and that distance is 1 or 2 positive or negative standard deviations away from that mean. So here we're looking at the difference between mu minus some z-score times sigma and mu plus some z-score times sigma. Now it's shown here as symmetric, but it's usually not that we're interested in. So forget that idea right away that it'll always be between one standard deviation to the left and one standard deviation to the right. So most distributions have an approximately normal distribution, which allows us to use this technique. And there are some distributions which don't, but under certain conditions we can use a normal distribution. And those conditions are quite easily met. Sometimes it's just having 40 samples in the, or 40 items in the sample we're looking at. So just having a certain number of them will make it work. So we're going to have a table at the back of the book if you look carefully. I'll give you a paper copy. It's called a Z-table. And we're going to learn how to use that in class. We're going to do a lot of practice. That table is also hidden inside your calculator in the programming, so we'll learn how to use your graphing calculator to do this as well. And quite frankly, sometimes the paper is faster. Sometimes people like to simply use the calculator as a check, so we'll do both. So you can check one with the other quite easily. So this is a partial copy of the table. You'll see how you have a z-value. So if we're looking at the z-value of 1.43, we come down the leftmost part, we come to 1.4, and now this is underneath 0.00, so this is 1.400, and you have a probability of 91.92%. If we come over here and come down, we have 1.4, and it's basically plus 0.03, so that's 1.43, and it's a probability of 92.36. Now what does that mean? If we're here and we're at 1.43, we're talking about the area under the curve from here all the way to the left. So it includes everything from that number we have all the way to the left. And that doesn't sound useful, but it turns out to be extremely useful. So there it is shown, particular. Now, if I actually know that, I'm going to click again to make the cursor appear, so I have to click and then go back. Maybe I want to know it from here to here. So if I can find this one all the way to the left, and then I can find one from here all the way to the left, and subtract one of those probabilities from the other, then I found exactly what I'm looking for. And we'll get to where you can see a picture of that. Here are the tails. Refresher on how to find Z. You notice that they're not using X bar, they're using mu. They're not using S, they're using sigma. The Z-score found for a population rather than for a sample is done exactly the same way. Now you do have to write the correct formula when you're showing work to show that you know you're working on a population or to show that you know you're working on a sample. So here are some examples. Suppose you have two standardized tests for the getting into college, the SAT and the ACT. And they give you the mu and sigma for each one. They just somehow know this. Well, how do they know it? Well, in this case, they actually do because they run the test and they have all the results, meaning they know the true population mean and the true population standard deviation. So how do you compare the ACT and the SAT to see who did better? Well, we compute the Z-score for each, and you see that the one on the left for the SAT is 1.5 standard deviations to the right of the mean. This is 1.91 standard deviations to the right of the mean. Now, we're looking at how many people did this individual beat. He beat everyone who was below 1.50, and this other person beat everyone who was below 1.91. So the one on the left actually did not beat as many as the one on the right. And we'll see if we can get a picture of that up. Nope, let me swing it back here. All right. So if you're at, say this is 1.50 and this is 1.91, this person beat all of these. This person who was to the right of it beat all of those plus a little bit more. So they actually did better, and that's how you use it. So we'll do a bunch of practices in class. Make sure to bring your calculators for this too. I will provide the tables for you.